All right, I want to take a look at what the derivative can tell us about the graph um, and some terminology that comes out of this here, some definitions. Here's a function I want to take a look at. Now, one of the things that I do every time that I'm graphing is I look at what does the function tell me before I even do any calculus. And with a fraction like this, numerator and denominator tell me a lot of stuff. Numerator tells me x-intercepts, so I know, for instance, there's an x-intercept at 0. Um, Denominator tells me vertical asymptotes, but the denominator is never negative, so there's no vertical asymptotes here. There is, however, a horizontal asymptote because the power in the numerator is at 2, the power in the denominator is 2, numerator is 1. So the bigger denominator, when x gets really big, the denominator is the big one. I find it easier to think over on the positive side here. When x is positive, numerator is positive, denominator is positive. So it's going to approach that horizontal asymptote like this. Likewise, on the negative side here, when x is negative, the numerator is negative, but the denominator is still positive. That negative squared is positive, plus 9 is positive. So negative divided by positive is negative. So it's approaching that asymptote on this side. So it looks to me like, the graph has to look something like this. There's no vertical asymptotes. There's one x-intercept. There's that horizontal asymptote of 0. So I got a pretty good idea what it looks like. Right. What I don't know is I don't exactly know where the highest point is here or the lowest point is there. Well, that's what the derivative is going to let me do, right? So let's do that. So y prime equals the derivative here. I'm going to use the quotient rule. X squared plus 9. X squared plus 9 squared, right? So x squared plus 9 times the derivative of the top. Actually, I'm going to factor that 12 out of everything. I want 12 times this whole thing. And the reason I'm doing that is the derivative of a constant times the function is the constant times the derivative. And I just don't want to, I know I'm going to have to do some factoring here, and it's just going to be easier to do it to start with. So the 12's there, so there's the bottom. So I'm thinking just as the x is the top here. So the derivative of the top is 1 minus the top times the derivative of the bottom, which is 2x. Right? If I hadn't left that 12 in there, then that would have been a 12, and you'd have a 12 here, and anyway. So the derivative here is 12 times, it looks like an x squared plus 9 minus 2x squared on the top, and an x squared plus 9 quantity squared on the bottom. The x squared minus x squared cancel out. Well, it's just a minus x squared. So I've got a 12 times 9 minus x squared on the top and an x squared plus 9 on the bottom. What I'm looking for is, where are those critical points? Where's the max and the min? So we have critical points. If either the derivative is equal to 0, 1, or 2, the derivative doesn't exist. Well, the only way the derivative couldn't exist here is if the denominator was 0, and that's a possibility, but it doesn't actually come to fruition because the x squared is always 0 or bigger, plus 9, that's always 9 or bigger squared, that's always 81 or bigger. This denominator definitely is never 0. So critical if the derivative is equal to 0 here. So I've got 12 times 9 minus x squared over x squared plus 9 squared equals 0, which divide by 12, multiply by the number, it's the numerator that's got to equal 0. So 9 minus x squared equals 0. Either think of this as factoring it or whatever. I guess I see it either way. This is 3 plus x times 3 minus x equals 0, so x equals 3 or x equals negative 3. So now, looking back at my function here, my graph, I know that this is at 3 and this is at minus 3. I can now plug them back in to see what I get for a function value. So if I plug a 3 in here, that's a 36 on the top. And a 9 plus 9 is 18. 36 divided by 18 is 2. So the height here is 2. Likewise, plug a negative 3 in. I think you'll see this is negative 2. Okay. Now, so what has this done? This by finding the critical points, it shows me exactly where the highs and the lows are. So my graph, although I had a good idea what it looked like, now I know I have an even better idea what it looks like. Now, let me show you what most calculus textbooks do at this point. It's like they think you don't know what the graph looks like. They say, well, we found two critical points. How do we know whether they're maxes or mins? Look at the graph. This one was the max, that one was the min. That's the way I do it. But here's what they, just to explain what they're doing in the book. They say, we're going to look at the number line. Here's my x-axis now. -3 and 3 are the points that have some significance to the derivative. So if I'm looking at y prime here, the derivative is 0 here and there. And the question is, in between, the in between those two and on the outside, so there's 3 pieces that the line gets cut into. Look on each piece and see whether the derivative is positive, negative. This is where it's 0. Well, if I've got a number bigger than 3, then x squared is bigger than 9, and this numerator is negative. So the denominator is always positive, right? So this derivative, I guess this is y prime right here, right? I guess that is too. So the numerator is negative, the denominator is positive, the 12 is positive. So I'm looking at a negative derivative. Now, what does a negative derivative mean? It means the function is going downhill. One of the words that they use here is decreasing, right? Decreasing function. When we now pick a number in between -3 and +3, then x squared is going to be less than 9, and the 9 minus x squared will be positive. The denominator is always positive, the 12 is always positive, so it's all positive. So we're talking about positive slopes here, and this is going upward. Well, upward, and this is what's called increasing. So to the left of 3, it's increasing. To the right of 3, it's decreasing. There must have been a local maximum at x equals 3. Okay. That's the argument that they're making, going uphill at 3, downhill away from 3, and so there was a maximum here, right? Likewise, now we go over here. If I get less than -3, like -4 or something like that, when I square that, that's going to be bigger than 9, and the 9 minus that thing is going to be negative. Denominator is still positive, the 12 is still positive. So this whole thing will be negative again out here. So my derivative is going negative to 0 to positive to 0 to negative. And so this is headed downhill. This is decreasing on this part. And so this right here, decreasing and increasing, must have been a min. Okay, so even if you didn't know what the graph looked like ahead of time, you could use the information from the derivative to find the critical points and then look to the left of one critical point, to the right of one critical point. Is it decreasing and increasing? It's a minimum. Is it increasing and decreasing? It's a maximum. Okay, so this is what's called the first derivative test for maxes and mins. Once you've found your critical point, look to the left, look to the right, see what it's doing, and you'll be able to tell the difference between a max and a min. Okay. Personally, I think this is kind of overkill if you already know what the graph looks like, which I did. I didn't use a graphing calculator. I just used my knowledge of what functions are doing and numbers are doing for different things here. Okay. One of the things that you'll be asked to do in the homework problems, whatever, is to state the intervals of increasing and decreasing. So I would write it like this. I would say this function is increasing. Oops, see if I can spell increasing. Probably not. Increasing on the interval from -3 to 3. Right? That's interval notation. And this is decreasing on the interval from -infinity up to -3, unioned with the interval from 3 to infinity. Okay. Intervals of increasing and decreasing. One thing I want to say about this too is be a little careful sometimes. If you had an example like this where let's say y equals 1 over x, right? which is just x to the negative 1 power. The derivative here is negative 1 x to the negative 2, which has one critical point, because this is minus 1 over x squared. This has a critical point when x is 0 because the derivative isn't defined at that point, right? And so when I look at that here, saying 0 is my critical point because the derivative doesn't exist at that point. But if I look to the left or to the right of it to see what's going on, plug in a positive x, this is negative. Plug in a negative x squared, that's positive, divided into negative 1, that's still negative. So this is headed downhill on both sides of 0. I would not, however, say this is decreasing on minus infinity to infinity, because there's this spot here where it breaks. I would say this is decreasing on the interval from minus infinity to 0, and then again from 0 to infinity. But at 0, it's not increasing or decreasing. It's not defined. In fact, the graph of this thing looks like this. So you got these negative slopes here, you've got these negative slopes here, but certainly going from here to here, you've got a bigger x value. I mean, you didn't go downhill from here to there. You somehow jumped up. So it's not always decreasing. It's just that there's an interval where it's decreasing, and there's another interval where it's decreasing, and there's a break right at 0. Okay, so I just want to distinguish that. Okay, next we're going to have to look at what the second derivative tells us about the graph.